Okay, welcome to office hours tonight. We're going to have a quick overview of the project and the assignment that's due tonight and the assignment that's due Friday. And so let me share my screen and we'll get right to it. And let's see, I have my little outline here. Let me share that with you guys. So you're supposed to calculate the heart rate using peak find for the homework tonight. And then on Thursday, I am going to release in an announcement to you a link to critique, I misspelled it there, it's called critiqueio.io. And so you'll get an invitation to sign up for Critique.io for Project 1. And you will submit your project to Critique.io. And it's a peer review. So we'll do a similar peer review. There'll be a rubric that you'll grade students to. I will grade some of the projects, and then you need to grade as if you were me. And if you deviate away from my grade, then you'll be counted off. So you have to kind of grade like you're acting as me as a grader. That's the way I kind of describe it. And what happens is if I grade student A and you grade student A and we're off, then there'll be some subtraction, right? But if you're very close to my grade, then you will not have any points taken off. So that's kind of how it works. So it's kind of cool. And you'll get to review other people's code and hopefully learn something in doing that as well. Friday, we will meet as a team. I know the afternoon has been kind of called off at the university, but our class is at 11. And, you know, I think these pseudocode sessions are really good. So I encourage you to come and we'll break up into teams and you will work on the pseudocode or project for Project 1 or do a flowchart. And so I'll give a little introduction and here's kind of what the goal is. You can read about the project on Critique and then come prepared to work as a team on the flowchart. And I think Victoria, you asked this question, are these assignments helping us for Project 1? Yes. So really these assignments you will then integrate into one larger project that will calculate the low activity periods over the 8-day period that we looked at, the 163 files, and then display and graph different things that I asked for. So that is the project, okay? So you've been working on the project through these assignments. And I had to do this. I didn't really want to do it. I think you'll have to work some over the July 4th, maybe work some on Friday, some on Saturday, take a little time off, and then you can have a couple of days to finish the project. I think it's a pretty complex project. When you get to start putting all these pieces together, you have to know how to program to do it. So that's the goal. I'll stop there real quick and see if there's any questions, and I'll go over a couple of points to help you in your assignments that are due today and on Friday. David, do you have any questions?
For the assignment due tonight, do we have to make a function?
I don't know if I asked for that or not. Did I ask for that in the assignment?
No, but I noticed that you made a function.
Yeah, I tend to make functions. I don't think I asked for that, but yeah, it's not required. If you didn't do it, it's okay.
Okay,
Now,
thank you.
in your project, you probably want to make it into a function so it's modular and you can use it. So that would be the other thing, is you might as well just go ahead and make a function.
Okay.
Okay. All right, good question. Thank you for participating. Anybody else? All right.
No. Output the heart rate for both the red and IR channel. Are we supposed to have two or the same?
I didn't catch the whole question. I believe what you asked, Alyssa, is do you need to calculate the heart rate for red and infrared? Is that correct?
Yes.
I think I just asked you to plot one of them, right? The IR. Okay, output the heart rate in beats per minute for red and IR. Yeah. Okay, so you output that to the console and then you can just graph the red one, okay? Make sense?
Yes.
All right, and yeah, of course, I've got, I have the graph here. Let's just open this and see what it looks like. Pretty cool plot. We got, goodness, went to the back. Okay, pretty easy little plot here. We got the stars and the dots. And I talked last time about how to get the troughs. You basically can just invert the signal, right? If you invert the signal and if you think about it, the troughs become the peaks. And now you can run you run the data through the peak finder again. You find the indices, and then now you can calculate the heart rate by knowing the indices values. All right, let's go over a couple things tonight, and we'll be real quick, and you guys can move on and work on your project or work on your assignment that's due tonight. Okay, let me back up a little bit. I had a couple of things. Okay, you've already done this one, which is find the most active hour. Oh, by the way, am I sharing? I'm sharing. You guys can see it, right?
Yes.
Okay. All right, and then I have this. I suggest you guys come up with this, this example here. Do something like this, where you can play around with the different peak parameters. Let's run this and see what it looks like. Okay, so, and yeah, here is the problem. I think it was Alyssa was asking. I plotted the standard deviation, only one data file, and then the heart rate. It's only one file that I just ran. And so it's not the standard deviation, but the mean that I plot. It's one data point. This one's more interesting. So can anybody explain what this little, it's not a spike, it's a dip. What is this right here? Should we worry about that? What do you guys think?
I thought it was just like where the time started, like when we started tracking.
Yeah, it's really an error in the data file. The first value is like 60,000, and that happens on every file. So you can discard the first few points from every file, but actually, when you start looking at the heart rate, it turns out the way the find peak works is that it doesn't find that peak because of the parameters that you set. So you can disregard the first couple of points, or you can use it. It doesn't seem to matter in the calculations. So that's what that thing is right there. It's just how we collected the data. There was an error in the data collection system, and the first value was an error. Can't remember if it's the first or second, or 1 to 3 values for an error. You can zoom in on it and look. Let's do that. So how many data points is this? I think it's just one. I think it's one data point that's wrong. So that's what that is, if you were curious about it. Okay, so if we ran this, actually had more data that we covered here. So I'm just going to start file 6 to 10. Let's do 6 to 10 and see what that looks like. And plot the results. You see it on all of them, right? What do you think happened right here between these two? So that's a discontinuity. That's kind of weird, right? Any guesses? Okay, this is actually a optical sensor. It's kind of like a Fitbit on the cow's ear. Any guesses for what happened right there?
The cow was moving.
The cow moved, so this was collected. So we collected, I believe it was every 40 minutes, we collected, so many samples. And so from this time stamp to this time stamp, there was some time involved and the animal moved. And now the sensor is on a different part of the ear and the measurement is slightly different. The DC value, the offset from 0 is slightly different, but it still picked up the heart rate, right? You can still see the heart rate there. So it's slightly different measurement. Ooh, this is pretty noisy, right? That's kind of an ugly signal. So that's what's going on in the data. And so the objective for project 1 is like, well, when should we actually do the heart rate calculation and when should we not do the heart rate calculation? That's the whole goal. And what we're going to do is use the accelerometer data to understand when the animal is moving, and don't calculate the heart rate then. And then when the animal is not moving, quiescent is what I like to call it, when they're still, we will calculate the heart rate. So that's the goal of the project, okay? So that's kind of interesting to look at. And notice that their heart rate's kind of moving around here over the data files. And that could be because the animal's moving and we're detecting heartbeats that aren't really heartbeats. So how can we come up with a method to reject the time when the animal's moving around? Okay. So that's kind of what we're trying to do here. So we're going to use this peak fit algorithm. Okay, so I've got one data file in here. This data file is kind of interesting. Data file 10 is the one I'm going to load up here, and let's look at it. So what I did in this chart was to find the peaks and the troughs and do all the stuff that you guys are doing for tonight. But then I also plotted the magnitude of the accelerometer data. And I added a DC offset of around 200,000 to make the data line up with the heart rate data. And you can see, like, we had this big spike in here. And if we zoomed in on this, maybe, it missed the peak. The peak is off because we had this acceleration data. So that, how do we reject that? That becomes the question. So that's what we're trying to do. All right, does that make sense to everybody? Okay, notice I labeled this down here, 1 sample per 10 milliseconds, which is 100 samples a second. So that's how fast we're collecting the data, okay? Cool. All right, so that's kind of a cool kind of concept to understand. And then the next thing I think that's important to understand, let me pull this up. I have a slide on it. Bear with me, guys. Okay, so there's a set of slides in your assignments or in your homework where I kind of walk you through what we're trying to do here. Okay, the tag is on the ear, the animal moves around. You guys can read all that, and then here's the motion spike, and we don't want to collect that data. So what we're going to do is we're going to figure out an algorithm that says reject the signal. If you see a motion spike, reject the signal. And so what I've done here is I've plotted the periods of high activity as set to 0. So if this is the normalized magnitude, and we've discussed what the normalized magnitude is, you do the magnitude calculation at every point, and then you divide every point by the mean magnitude, and that makes everything around 1. And what we're going to do is set a threshold. Anything above that threshold, like this one right here, we're going to say, reject all of the data around that spike, and then and don't use that to calculate the heart rate. Okay. So that's what this is. And out of all this data, if we use 10% as our threshold, it only found these 2 sections, this section right here and this section right here. So all of these kind of spikes went barely above the 10% number, and here that is. So if you kind of zoom in on this, this is a high activity, 10% above the normalized magnitude or 10% below. If we get any spike, we're going to reject the time, that point and the previous 1,000 samples or 10 seconds of data, because we're sampling at 100 samples a second. I'll stop there and let you absorb that and see if you have any questions. All right, you guys are sharp, no questions. Either that or I'm putting you to sleep. Oh, no. Okay, so you have to understand this idea of a moving window. So we're going to think, if you think about, if we took 1,000 samples and we scanned along this 1,000 samples, and then I was looking back at every sample, I looked back and said, is is there a sample that went above the thresholds or below the lower threshold? And if so, we're going to reject those 1,000 samples. We just do that all the way through all of the data. So that's the idea of a moving window. And just a little bit about moving windows, you can have a moving window that kind of jumps and it has a 50% overlap. So this is our first moving window. And then we jump 50% and then we do another moving window. Or we could have a 10% overlap. We have a block of data that we're going to analyze and then we jump and then there's a 10% overlap. What we did is, in my examples, I've suggested use 100% overlap. So we're just going to analyze data and then we're going to move one sample and then analyze that whole period again. Now you may be able to come up with a more efficient way to do that. This is not the most efficient way to do it. I think it's just an easy way to explain to the class. So if you want to improve the performance of your project, you will focus on things like this. Because you could just say, if I've already analyzed this window and I move one sample, why don't I just analyze the one sample? So you might look at that as a method. So what happens is if you zoom in on, I can't remember which, this is data _6 to 10. We got a sample that went underneath here. So there was one sample. We come back up here. This is kind of cool. We come back up here. There's one sample that went below the threshold, and that's this guy right here. And so it basically said stop. So now if your data could, so you're moving over, you're moving windows 1,000 samples wide, but then if you go to the 1,001 first sample and all of the samples are good, you want to keep that record to be 1,001. And so you could have a very long record that you're going to analyze for heart rate that can be longer than 1,000 samples, right? You just want to keep growing the record of data that you want to analyze until you reach a point where, oh, there's a data that's outside of my thresholds, and now I'm going to reject that sample. And then we start over, start looking at 1,000. Is the data within the threshold? And start over again. So the constants that you need to know, the 100 samples a second. A low activity period is defined as a magnitude that's between 0.9 and 1.1 of the mean magnitude. A low activity period is defined as 10 seconds of low activity. So you need to read your files, calculate the magnitude, calculate the mean, normalize, assign what I call a look back. That's what I call it, a look back window. I'm going to look back 10 seconds, 1,000 points. And then you could make this a user-defined function. So this should not be a hard-coded constant, because I might say, oh, I might want more data for my heart rate analysis. I want to look at 6 seconds, or I want to look at 20 seconds. You know, to have even a more, maybe a more restrictive assignment to data that I want to analyze for the heart rate. All right. A biomedical question for you is, if you know that the heart rates of these animals, they're kind of like in the human range, but maybe a little bit lower. Let's just say that these cows, their heart rate ranges from 60 to 120. What is the minimum time or amount of data that we should analyze to get a beats per minute? Anybody have a thought on that? Really, to kind of answer this, you probably needed to review my video for the introduction of the Spo2, how to make an Spo2 measurement. It's kind of intuitive, right? Anybody want to venture up a guess with some logic about, well, how big should this window be? Is 10 seconds arbitrary? Could I have half a second window? All right, I'm asking you guys to think and speak up. Anybody do I need to have you put it in chat? Okay, David, thoughts on that? Hello, David.
Yeah,
Yeah, thoughts on what's the minimum window of data we should look at? Could, we selected 10 seconds. Could we have looked at a half a second? Any thoughts on that? Anybody else want to venture a guess? Victoria, I saw you were about to speak.
Well, I'm not exactly sure, but I was just thinking for the SPO2, would there be, like, it's because I was wondering if it would make more sense to do like 0.1 seconds, because it would be better since you're collecting more accurate data, but I'm not sure on how like it'll affect it exactly.
Yeah, so the SPO2 measurement requires you to have a pulse. Because you're looking at the AC signal, which is the envelope of the pulse, right? Let me give you a couple of definitions. Actually, we're going to cover this on Friday. Let's see, I don't think I have it here.
Oh, sorry, Professor Hanks, I was just wondering, would this be the same? I guess would the look back window have to be at least the length of a pulse cycle to get accurate data?
Bingo, that's it. So yeah, so if you're calculating beats per minute, right, and the animal's lowest heart rate is 60 beats per minute, so that means there's one cycle every 1 second, right? And if you collect less than a second, then you won't get a whole cycle. So you won't be able to calculate. You won't be able to find the two peaks to find the beats per minute. Okay, does that make sense? All right, and you probably want it to be longer than that so that you catch a couple of cycles so that you can have a more accurate calculation on the beats per minute. So the minimum time would be a second, but you're kind of risking it a little bit. Right? So that's the reason for 10 seconds. I don't think we could go less than a second because we need to get for beats per minute, because the animal's lowest heart rate's about 60. Okay, so that's kind of an interesting thing to think about. Now, I would encourage you to go back and look at the video on the introduction to how to make an SPO2 calculation. And I talk about what is an AC signal and what is a DC signal. And you need to kind of know those definitions to do the final part of the project, because the definition of how to calculate the SPO2 is the AC of the red signal over the DC of the red divided by the AC of the IR over the DC of the IR. And that's a ratio of ratios is what that's called. That's in the video. I direct you to do that. But all of the coding that we've done so far is setting us up to make those measurements, okay? All right, so I wanted to give you guys an introduction to that. And then let's see, I had a couple of other pieces of code to show you. Let's see. Low activity periods. Is that the one I wanted to show? I think so. Let's run that one. Okay, yeah, we just went over this in that presentation. There's only 2 low activity periods. Let me go over the code because this is really important. I've got my user inputs here, sampling rate. Look back time is 10, which is in seconds. And then I've got my threshold at 10%. I might want to set that to 20 or 30, depending on the application. You guys know that part. So here's where I do the calculation of the mean. Notice that I'm using my NumPy, so I get better performance, right? And then I have my upper and my lower threshold. upper threshold is 1 plus the magnitude threshold, lower threshold is 1 minus the magnitude of the threshold. Then I defined my look back samples, which is the sampling rate times the look back time. You probably could have just made that a constant up here, but just to make sure everybody knows what that is, I put it into my calculation. So I could change my look back time and my sampling rate, and it would automatically calculate that for me. So I got a little fancy there. So I created a variable called Q, which is quiet. Q is for quiet. And I'm going to say, I'm going to set up an array with Q, a NumPy array. It's a bunch of, that's the size of my magnitude calculation. So I have basically an array with an element for every index that's in magnitude. And then I got a little fancy here. I said, okay, I'm going to use this thing called enumerate. And what enumerate does is it returns the key and the value of the magnitude. So I get the index and I get the value. And then I say for every V, every value that's in between my upper and my lower threshold, I'm using conditionals here, less than or equal to upper threshold and greater than or equal to lower threshold. It's an and, so it has to be both of them. I'm going to set that value to 1. Okay. So that's a low activity period. Quiet, true. Quiet equal 1. Q equals 0 is for the high activity periods. Not quiet is set to 0. Okay, and then here's where I start my moving window. I'm going to start from I, and then I have my look back samples. That's in my range, so that's where I'm going to start with. And remember, that's 100 samples a second for 10 seconds, so it's 1,000 samples. I'm going to start at sample 1,000, and then I'm going to go to the length of my quiet, and I'm going to say I want to put the Q window, and I want to look from I, the current I that I'm on, back 1,000 samples. So 1,000 samples ago to the current sample, and I want to test, is there any non-zeros in there? Does that equal 1,000? And if so, I want to set this Q final equal to 1. And so that's how I calculate the low activity period. Because low activities are 1. All right, so that's a little complicated. You're going to have to think about that. I believe, I know there's a better way to do this. I've given you one way, and I'm hoping in your project you will do it a better, faster way than I've done it. That's really kind of a part of the project, okay? And then I plot all these results. That's what we did in that code. All right, a little bit about moving windows. I had a little sample here, some moving average code. This is one of the samples under the extra exercises. And what I did with this one is I loaded in Apple stock price. And if we plotted this is kind of cool. We can look at the stock price. So this is kind of another example to look at. So this is what a moving average does to your code. So the orange line is the raw data, and the moving average, I think I looked back 10 days. I can't remember. Back 10 days, let's see. Yeah, number of days, I'm going to look back as 10 days. And then it plots the average of the past 10 days at the point for the blue line. So the blue line is actually looking at the orange line, the last 10 days, and averaging it. All right, so you can kind of see that, right? If you go back 10 days from that point right there, oh, that looks about the average. There it is right there. So what happens is if you do this moving average, you end up smoothing out the signal, right? This is smoother than the raw data. And this is a filter. You're going to learn about this in your signal processing class. This is a very simple filter. I'm just removing the noise from the signal. Okay. This is not a signal processing class. We're not going to go into all that, but it's kind of an introduction to, oh, we've just applied a low pass filter to this to get all the noise out of the signal. I just averaged the previous 10 days. And that's a very simple version of, in a generic term, a low pass filter. Okay, I am going to stop here and say, let's see if you guys have any questions. I think I've given you enough of the background information for you to solve the problem tonight and turn that in. And then I encourage you on Friday to show up at 11 a.m. We'll break up into teams. Come prepared and read the background documentation about the final project. There's a presentation on that in the modules in slide form, as well as I will have critique updated with all the rubric on critique so that you can review that. If you come prepared, then we can work on, and as a team, your pseudocode, but then you have to code the project yourself. And the assignments that we've done to date are building the modules that you will need to integrate into the final project, project one. All right, I'll stop and be quiet, see if there's any questions. Okay, really smart group, no questions.
So for the alternative moving window, could we use, because I know Pandas has a moving average. So do they have a moving window?
Possibly. What I did is just use NumPy, right? And part of the, maybe this is a little bit of an academic thing. It's like, hey, I want you guys to get used to using NumPy because that's the power of Python. If you can find a better way to do it, I'm fine with that. You know, that's great. There's a moving average, but we're not actually, I showed you the moving average as an example of a moving window because we're not applying a moving average. We're just looking at a moving window. So a moving average is kind of like a moving window, but it's not the same thing, right? We're doing a different processing activity on a moving window than an average.
Okay, thank you.
You're welcome. Fazul, any questions tonight?
Not particularly.
Okay. All right, that's all I got for tonight. I'll hang out if anybody has a specific question or, you know, I'll be here for a while.
Thank you.
All right, take care, guys.
Thank you.
See you, David.
Actually, Professor Hanks, I was wondering, so all of the functions that we've been doing for the project so far, I've been putting them on one file. Do we make multiple files for each function that we make, or did you want us to stick with the same function and just adjust the bounds?
I think you can just keep them all in one file. That's fine because ultimately your project is going to be in one file.
Right, right.
Yeah, and then you can call you might have to change them a little bit to make them into functions so that your code is readable. That's one of the things in the project that you'll do is take what we've done and make it into functions so it's modular so that somebody can understand it, right?
Mm-hmm. But I guess for today's assignment, I like reused the same function that I did to read files, and I just adjusted the bounds for it to be only file 6. But I was having issues, I guess, copying or plotting the data properly because it plotted all of the read data instead of just for file 6. So I think it might have been an error. Like, would we be able to make a new function for this project, or would it have to be the same as the first?
You could create a new one for this assignment. Okay. And then when it gets to the project, you'll have to fix all that, right? Make them into
just one
functions. Yeah.
Okay.
You want to look at your plot now and see if I can help you through that, or you already submitted?
Sure.
Okay.
No, I haven't submitted already. I'll go ahead and share my screen.
Okay. Oh, I need to stop sharing. Give me just a second. I'll stop recording so that we can just have our discussion here.